So for our next talk, we have another pioneer of empirical evaluation of machine learning, Professor Isabelle Guyon from University of Paris-Sud. Thank you for coming.
Thank you for the introduction, and thank you very much to the organizers for inviting me. It's a great pleasure to be with you today. And the talk today is going to be about neural solvers for power transmission problems. So my name is Isabelle Guyon, and this work is the work of my two graduate students, Benjamin Donoho and Balthazar Donoho, and in collaboration with their co-advisor Antoine Marot, who is engineer at RTE. RTE is the French power transmission operator, and is helping us turn on the light every day. We take that for granted. We think that, you know, electricity is some natural commodity to have available to us at all time. But it's actually a great deal of work for many people to make that happen. Andrew Nguyen is credited for this quote that artificial intelligence is the new electricity. But is there a symmetry? Does it mean also that electrical power systems are intelligent in some manner? It's not clear, at least at this stage. And they are certainly very complex artificial systems, but it doesn't necessarily make them intelligent. Unfortunately, we are all too familiar with the fact that sometimes electricity goes out. And how does this happen? Well, it could happen that, for example, in a thunderstorm, there is a line that goes out because a tree falls on it. And when that happens, the electricity must be rerouted in all the other lines on the grid. And of course, then there is a surcharge on all other lines. And it might happen that one of the lines also goes over their thermal limit and breaks. In that case, even more electricity gets spread out over all the rest of the grid, and there is a domino effect which results in a blackout. So are blackouts thing of the past? Not really. Currently, at least in France, there are lots and lots of control rooms. There are rooms filled with screens, and highly trained engineers at all times watch the network and control it. It's believed that if they would stop working after only 2 hours, there would be a blackout. And their environment is rising in complexity because we have now renewable energies, which are less easy to predict. You never know, when wind is going to blow and when it's going to be sunny or not. And governments impose that renewable energies be used in priority. There's also difficulty linked to new types of uses of electricity, like electrical cars, and also the globalization of the market of electricity. Now electricity flows throughout Europe, and when the south needs electricity, it can come from the north, and then the grid in the middle, which is the French grid, gets overloaded. And in parallel to that, it's becoming impossible to build new lines because, in fact, consumption is not increasing, so there's no budget for building new lines. And in any case, nobody wants more lines in their backyard. So in that context, the French power operator, RTE, is very actively doing research to operate the grid in a more effective way. They collect a lot of data, some of which they make available to the public, even in the form of challenges. And they actively work on better visualization tools, but mostly they're interested in not losing the opportunity of showing that machine learning can make a difference. So they've been launching a program in machine learning, both doing imitation learning to try to imitate what the operators currently do, and reinforcement learning to do even better control than what the current operators do. And these are the two PhD theses of my students. And the problem of controlling the network is, we think, so hard that actually we decided to have the entire community help us solve it. So we designed a little game, and it's going to come out as a challenge in May. And in this game, what you have to do is to maintain the grid in security for as long as possible and avoid blackouts. Currently, the game is only going to be for a 14-node little grid, but we're going to scale it up over the years and hope that as many people as possible will try to help us solve this problem. But for this talk, I'm not going to be talking about that. I'm going to be talking about an easier problem that's a building block that we've been trying to solve recently. And that is the problem on only predicting what are the power flows in all the lines. So on these very small toy problems here, I'm illustrating what we actually want to do. The inputs to our prediction system are the so-called injections, which are productions and consumptions. So productions are the electricity coming out, of the windmills, the thermic centrals, and everything. And the consumptions are, what we consume. So they're all the inputs to the grid. And in blue, you have all the lines in the grid, the transmission grid. And the goal is to predict what are the power flows in these transmission grids so that when we want to avoid overheating, we can take actions on the topology of the grid to avoid that there is any overflow of electricity in any part of the grid. So in order to solve that problem, currently, RTE and other transmission operators use numeric solvers that are based on solving the differential equations of electricity. And the idea is to replace that by neural network emulators with the hope of speeding up the prediction. So the current numeric solver is based on the equation of physics. It is relatively slow, so it doesn't allow operators to simulate a lot of situations. Obviously, you don't want, to make an action on the grid that will result in worse conditions than what you're actually in. So before doing any action on the grid, it's simulated. And in order to take the best possible action, the operators must simulate lots and lots of conditions, and often at night in prevision of what's going on the next day, because there are, meteorological weather predictions. There are also maintenance that are planned, etc. So at night, a lot of proactively, cases are being simulated. And the nice thing about the solver is that you can simulate all sorts of different things and see whether they are likely to improve or make things worse. Well, what we want to do with the neural network is to simulate some of the conditions that might be hard to simulate with the actual solver, because they require multiple changes. So what we want to do is we actually want to do a lot of simulations with the big simulator, and we want to train the network, the neural network, to imitate. So the easiest way of doing that is to put the injections and the changes in topology of the grid at the input and to predict the Y's. And we've been investigating an alternative architecture, which consists in actually injecting inside the latent space, let's have a pointer. In the latent space here, we inject the topology information. The way it's done is quite simple. We have direct connections between the first hidden layer and the last hidden layer, and those account for what we call the reference topology, in which usually the grid is operated. And then there are additional neurons here that are turned on and off, and that express modifications in topology that the operators do on the real grid. So we compare these two alternative ways of encoding topologies. We actually call this network in which we encode the topology changes in the middle a leap network, because it's like making leaps in latent space. And compared, to the solver of the differential equations of physics, it's quite a bit faster, particularly because we can simulate it on GPUs. And so RT is quite hopeful that this will help speed up the search for different alternative solutions of modification of grid topology that would solve problems proactively. And right, so it's able to predict not only changes in topology that has been trained for, but actually combinations of changes. And I'll come back to that in just a minute. What it cannot do really well is predict under completely different architectures of grids. So it's looking around a reference topology of the grid for little changes. So more concretely, here is what happens. So here you see a very small example of grid again with some injections and some consumptions. And imagine that at some point in time you have one line which is overheating. So the operators might take an action in order to correct that. And they will try to reroute the electricity in a way that no line is overheating anymore. And in the French system, there is a possibility of actually splitting nodes. So this substation here, in which there were all these different lines converging, you can split it into two different nodes. And in that case, you solve the problem. There is now the amount of electricity flowing in this line goes below the thermal limit. So these are the kind of actions that the operators do on the grid, and they're coded with numbers. And the rule of the game that we are playing is that we can train the neural networks for single such actions, and then we ask the neural network to try to generalize on combinations of actions. And since, of course, it's a combinatorial number, it's very advantageous to be able to do that. So here are some experiments. This is an unavoidable experimental slide in which, of course, everything works. So we did some experimental work both on synthetic data and on real data. The synthetic data came from a case that is standard, the IEEE case 118, which has 180 nodes, and it comes from a simplification of the California grid. Has about 150 injections and 200 power lines in it. And we also investigated real data, and the real data came from the Toulouse region. That's not that. Came from the Toulouse region of France, and it has about 400 injections and 400 lines. So in the synthetic data, the advantage is that we can simulate all different sorts of actions, whereas in the real data, we are bound to using only the action that actually happened in historical data. So in order to see whether the method worked and did what we call super generalized, that is generalized to new distributions of the tau variables, which encode the topology. In the real data, we used different mounts in different years. Whereas in the synthetic data, what we did is that it was trained, the neural network was trained on some injections and some topological changes that were, as we call, unary changes, so one node split at a time. And it was then tested on topological changes that were combinations of node splits, so it hadn't seen during training. And the interesting thing is that the neural network is capable of doing regular generalization, so generalize on the on test data that's distributed similarly as the training data, but also capable of super generalization, that is when tested on a different distribution. We compare with one baseline that's very commonly used in power networks, which is called the DC approximation. It's a linearization of the equations of electricity. And so both neural networks, the one that has the topology information at the input and the one that has it in the inner layer, perform well in regular generalization. But in super generalization, only the leap network, the one that has the encoding of the topologies in the inner layer, performs better than the DC approximation. And we have similar performance in the real data. But there in the real data, we cannot actually compute the DC approximation, because in real data, we don't have detailed information about what the topological changes are. We only have essentially an simplifier that is an abstract number. And so we can encode it in the network, in the neural network, but we cannot run it in the simulator. But what we can see is that the leap network performs better than the network that encodes the information as the topology information as an input. So we were quite happy with these results, and in fact, my grad student just graduated and was hired by RTE to continue on with this work and implement it in production. When my second grad student came in and said, oh, well, let's try something completely different. And in that case, he's tried to overcome the problem that we were working only around the reference topology and could make only some small changes. He said, why don't we do something completely different that allows us to work with any grid topology? And in order to do that, he replaced the original grid by a dual grid. And in that grid, each line, in fact, becomes a node in a grid. And the lines are interconnected between one another. And what we're going to try to see is how we can evaluate the flows in the different lines iteratively, basically mimicking the way the Newton-Raphson solver operates, but in a faster way using a neural network. And to map this to the previous notations, so here are now the injections. So these are the X's in our previous slides. And the power flows are now the values that are flowing through these different lines. And here is the new architecture. Now, at the input of a network, we put the injections, and for the power flows, we just put zeros. And then we let the network iterate a few times, and finally we read out the values of the power flow. So you can think of that actually as like a recurrent network that is unfolded in time and only operates a few iterations. And each line is actually recomputing its flow from information from its neighbors. And this new idea works also quite well. It has the advantage compared to the previous approach, the LeapNet, that you can now do more important grid topology changes. And here's the key experiment on that new architecture. Here what happens is that Balthazar trained on little power grids that have only 30 nodes. But then he could test on grids that had all different sizes of the ranging, from just a few nodes to more than 100 nodes, and he could still get very good prediction accuracy of the power flows. So this 0 indicates here 0 error, so this would be what is obtained by the actual physical simulator. And this is the DC approximation, which is the approximation that is currently performed by transmission operators. And this is now what the neural network does. So in conclusion, we've progressed towards reducing the burden of operators. And at this stage, the prediction accuracy that is obtained by the neural networks is good enough for deployment, almost good enough, I guess. It needs further testing on larger networks, but on small networks like the Toulouse region or the Marseille region, it's already been validated. And although the prediction of the flows are not as accurate as those of the physical simulator, they actually give very good ranking. So that's something that was mentioned several times in the past in previous talks, is that how accurate do you need to be in order to deploy something like that? Of course, you can't do any error that will put everybody in the black and lead to a blackout, but it's sufficient that you can rank all these different possibilities of topological changes in an accurate way, and then you put at the top those that are most dangerous to investigate or most promising if this is a curative action. And then those you can run through the actual physical simulators. So there is no risk. It's a win-win situation. You can combine the neural networks that provide you speed and allow you to rank the different situations, and the physical simulator that gives you accurate prediction. And with that, I want to thank you for your attention.